Good morning. I'd like to welcome you to CSCS. My name is Jean Favre. As it says here on the title, I'm a senior engineer, which means, what does it mean? It means that I've been here many years. Okay. I've done scientific visualization all those years, so I have a bit of practice. In years past, visualization was done in what we call the post-hoc paradigm, meaning simulations dump data to disk, and then at a later time you use a visualization application and you read your data back and you make your analysis. And if the analysis shows you that there's a problem with the code, then you go back to your code, you fix the bug, and you run your simulation again, and you dump your data again to disk, etc. So it's I don't want to say an endless loop, but it's a loop that you do multiple times until you have the right results. And doing this multiple time, which means that the I/O system is really stressed a lot, because the simulation dumps data to the disk. That's one. The visualization app reads the data back, and you do this many times. And then most often, at least in a supercomputer environment, simulations run at large scale, so maybe on thousands or more compute nodes. And then it was often the case that visualization resources were less than computational resources. So you would have to read the data back into a visualization application with less compute resources. So this has also been somewhat of a limitation of this method. So what we're going to talk about today is what we call in-situ analysis and visualization. And we're going to use two systems. One of them is Catalyst, and the other one is Ascent. So Catalyst is actually associated with ParaView today. ParaView is an end application which we will use at least for a few exercises today. By the way, how many of you here have used or used ParaView for your daily work? One, two persons only. You two doing fluid dynamics, you need to use ParaView. This is one of the best tools there is. We can talk about this. Okay. So ParaView is an end application, and at the moment we'll talk about what Catalyst is, but at the moment ParaView is the only application which can interface to Catalyst. But they're both actually made by the same people, the Kitware company in the USA, so there's a very strong binding. Ascent, on the other hand, is developed at Lawrence Livermore National Lab. And Ascent actually derives from, and the people behind Ascent are actually, some of them, people who were in the development team of Visit. Visit is another end application for visualization. How many of you have used Visit here in the room? One person. Okay. I will tease you again. You two doing fluid dynamics, you need to know about the Visit application, because it's also a very high performance visualization application for fluid dynamics and other scientific fields. Now both Catalyst and Ascent are using underneath an API called Conduit, and Conduit is really, the name is well chosen. Conduit is to bring data from one place to the other. And those two places can be two running simulations, so a data producer and a data consumer. And by the way, the data consumer can be a visualization application. So this is why we're going to do in situ visualization by intercepting data before it goes to the disk. In fact, we're going to limit the I/O to the disk to the strict minimum, because when you do large-scale simulation, what really kills the runtime of your simulation is the I/O. So, however, if you can access the data while it is in memory, there you have very fast access, and you can apply the visualization right there. So we'll see a bit more about this. Enough of this introduction. I will go through a few slides. So first of all, thanks to different teams, the in-situ visualization community now is pretty large, actually. There are very big actors, especially in the USA, Berkeley, Oregon, Lawrence, Livermore, Los Alamos, Sandia, and of course the Kitware company, which is missing here on my slide. Yesterday evening, 9 o'clock, I opened my presentation and, oh my gosh, all the pictures were gone. I had a moment of panic. I know I put the Kitware company, the name Kitware, those in my slide. It disappeared. I apologize for that. So I had to redo things very late last night. This is because I used LibreOffice on my Ubuntu laptop to edit the PowerPoint. Live dangerously. All right, here's the agenda. This is the welcome part, 9:30. This is what we're doing now. I have motivated the problem. I will show you about the technical details for login, etc. And then we will go on to introduce a bit more formally the in-situ visualization paradigm. We will go, before the coffee break, to Conduit by examples. So we're going to use Jupyter Lab notebooks to do this. And it should be very intuitive and very, very easy to follow. We'll have a coffee break, I hope at 10:45. If I run late, wave your hand, tell me that you need coffee to follow up. After the coffee break, we'll go into Ascent with examples, always using Jupyter Lab. All this until, with examples, all this until the lunch break, 12 o'clock. 12 o'clock, we're going to go out to the nearby restaurant here for Il Tagesmenü. Okay, that's the only German I will speak today. Afternoon at 1 o'clock, we'll go into Catalyst. So Catalyst is strongly linked to ParaView. So we will introduce ParaView first, and then talk about Catalyst, and then again show different examples. We'll have a coffee break. And then we'll go into some future development, and one of them, I've made the picture right here. Sorry about this. Right here on this board, I will discuss it a lot more in details at the end of the afternoon. But basically what this shows is the ability to, from a running simulation, to send data either to the disk during the traditional I/O, or to another simulation running on a different computer resources, or executing directly a script that ParaView will have developed for us. And all of this without recompiling the application. So this is a very interesting paradigm, and this is actually at the boundary of what we call in-situ visualization, because this is what we call now in-transit visualization. And we'll see this can have some very interesting usage. All right, technical details. So I've shared with you your login account for the course. So all of those accounts start with class 5, and then there's another digit here. There's a password which is dedicated to you. The first thing to do is to SSH to ELA, which is the front end to the supercomputer, so lab.cscs.ch. From there, you can jump into Daint, which is our Cray supercomputer. Now, I've logged in using each one of your accounts yesterday, using the password I had, to set up the account appropriately for the class. So I strongly advise you to use that account, even if you already have a computer account at CSCS for your own project, because this guarantees that the setup I have has been tested. Like I said, I bootstrapped all the requirements there on your accounts, and specifically that particular file here, home jupyterlab-cscs.env, contains all the modules which we will need to execute JupyterLab exercise. There is a reservation for computer node called In-situ, and this can be turned on if we require it. Those accounts will expire at midnight tonight. So if you do some specific things that you want to save before you leave the room this afternoon, do a backup of your data. My repository instead should not expire, at least as long as I'm alive. So let's hope for good. It has the name 2022 because this was started last year, and this is now something that we will continue. So I didn't care to change the name of the repo. I have already cloned that repo onto your account. So if you've logged in, you should see this In-situ Viz tutorial directory. All you need to do is change directory to it and do a pull for the latest updates. One of the updates, actually the only one I've done this morning since then, is that I've put the slides, the PDF of my presentation on the machine. And the file, which is called Pitts Daint Instruction 2023, actually shows you what I have done to set up the account. So this is not, it's just for your curiosity. You shouldn't have to redo this. Okay? Is it clear? JG actually is working in my own office. So if he misses the very first pages, I think he can catch up later on. So what is in-situ visualization? Why do we need it? I've already motivated some of that. There's a very nice book that you can download in a PDF here if you want to really dig deeper into the example. In-situ, puoi guardare questi due personaggi qua che non riescono a fare il login. Allora, in-situ visualization is nothing new. I mean, we've all done it, putting a printf into our code. This is actually in-situ analysis, right? Anyway, besides the joke, we've done it for many years with dedicated codes. More than 10 years ago already, there was a visualization library called LibSim, to which I participated in the development. This was integrated into Visit. This was 2011 when we developed that. So as you can see, time actually goes quickly, and things have been around for a while. Catalyst also has been around for a while. There was version 1 of Catalyst, which actually required you to know a lot about the VTK toolkit. So I've talked about VTK. What's VTK? VTK is a C++ library, which is actually the core engine of the ParaView and the Visit visualization application. So I will talk about VTK a few more times during the day. What I will do is actually also play back one of the presentation from the Ascent tutorial at Supercomputing 2021, and then we'll give more details about the two implementations. So today for the exercise, we're going to use SPITZ-DAINT, which is our current Cray supercomputing for production user. It's a rather old machine today, but still has over almost 6,000 compute nodes equipped with GPUs. So it's the machine that we will use when we log in to jupyter.cscs.ch. And then, since I said that this was a machine that is aging, we have a replacement for it. That replacement is called ALPS. This is the machine that will be given to the users progressively during the year 2023. Perhaps some of you already have some early access to the machine. So in the past, the prominent paradigm was post-hoc visualization, i.e. dumping data to disk, okay, at regular intervals. And for that purpose, actually, at CSCS, under this particular link here, you have more details about how to read back your data between after your simulation with those application, with those visualization applications. And here's actually the first problem. I said to read back the data. So the problem is the data format. I'm sure most of you have been confronted with the problem of which data format do I use for my application, and which one did my colleagues earlier use? Is it still a valid data format? Can I express all the particularities of my data using a given format? And if so, okay, I'm interested in astrophysics or fluid dynamics or geophysics, and my expertise, I'm speaking from your point of view, is the scientific domain. It's not writing I/O code. And I've seen it for many years, and I still see it today, people with the brightest ideas and the most efficient computer codes with very poor I/O strategies. Because I/O is just something difficult to do. We have to learn an API. How many here use HDF5? A few. How many people use NetCDF? None. How many people use Adios? None, etc. So those are different examples of strategies to save your data. When I say HDF5, actually, HDF5 is not a file format. HDF5 is an API to save data to disk. But you can save it in different ways. It's just like the natural language. Speaking English or Italian or German or whatever, you can express the same thing, perhaps in a with different verbs, different nouns, different adjectives, etc. And you still get the result. You still understand yourself, right? You still make yourself understood. Well, with data I/O, it's a bit more complicated. If you write data, your data arrays in a particular way, how do you expect the visualization app to read the data back? It actually needs to know what your intent was. So HDF5, the problem with HDF5 is that we need a convention to be able to read back the data. Same thing with ADIOS. Same thing with NetCDF. There's a very good example with NetCDF. The climate community, the people doing weather forecasting, they use a particular convention. Actually, the name, what is that convention called? I forgot at the moment. Anyway, there's a special set of convention, meaning that if people write NetCDF climate data, actually it's called the CF, that's what it is, the CF convention, climate data convention. And if you use that CF convention, then ParaView, Visit, etc., those different applications for visualization know how to read your data back. In summary, without I/O, no visualization is possible, and without I/O, you could not. What is the purpose of doing simulation if you cannot actually write the result somewhere? So the true cost of a computational cycle is really the simulation, and then the I/O, which you need to do multiple times between your simulation and your visualization app. Now, we have a dilemma here with simulation dumping data to disk. The first question is, how often can you afford to dump your simulation data? If you have an iterative process, perhaps it's the overhead of writing data to disk is too much if you write every iteration to disk. So it's very common to say we write every 100 time steps, for example, we write a solution to disk. The other thing is resolution. Can you afford to use the full resolution of your data to save your data to disk, or are you limited? And which variables in your code should you actually write to disk? Sometimes a single variable, maybe the velocity of your field and the pressure of your field is enough. But for example, again, the climate community, the people doing weather forecasting, they are used to dumping tens and tens and tens of different variables. So the data explosion is just becoming a bottleneck very soon. So there we have the decision between how many time steps to save and how many variables to save, at what resolution, etc. And that makes it pretty complicated. Alternative, save your data less frequently, but then you might actually miss some important feature in your data. That's really where the problem stands. With in-situ visualization, you now have the opportunity to look at every iteration step, at every variable that is active during your simulation, because you are dealing with the memory, with the data in memory. You are live with your simulation, and you already have all that opportunity. However, again, if you're going to apply a visualization algorithm at every time step of your running simulation, you will slow down the simulation somewhat. So there will be a new dilemma to go around. So here are some of the questions that have been raised in the last decade about using in-situ visualization. The first one is about sharing physical resources. If you're doing visualization while the simulation is running, you are perhaps sharing the same computational resources. Or perhaps you need an external or on the side another set of compute nodes to do your simulation. What about domain decomposition? Nowadays we do simulation across multiple GPUs, across thousands, millions of compute threads, is the same task decomposition that fits well for your simulation? Will that task decomposition fit well with the visualization algorithm? And often the answer is no. So there's a discrepancy between the efficient use of your GPUs, your CPU threads used by your computational kernels and by the visualization kernels. So this will have to be resolved. Again, is the visualization task something quick, or does it take actually more than an iteration step of your solver? You'll have to, there's a trade-off here, and you'll have to decide what to do. Since we are doing things on the fly with a running simulation, it usually means that the previous time step is not available anymore, okay, and so forth. So there are some algorithms which actually will be difficult to apply, algorithms which have to look at a certain number of time steps together to calculate some particular features. So this will be a limitation of in-situ. Now, the purpose of doing in-situ visualization is to actually do most of the heavy-duty analysis and visualization online, and then save to disk some data that occupies less bytes. So it's faster to write. Typical case is writing images. Images are actually just a few megabytes. Okay, think about HDTV resolution, for example. You have maybe between 5 and 10 megabytes of data per image, and that's it. Nothing to compare with saving 1024 cube of velocity data, for example. If you're saving less data, perhaps it's interesting actually to save some ancillary data, some context. How did those images get produced, and what do they represent? So this will have to be taken into account. And then what we really need is a more generic abstraction between data and mesh structures. There will be people doing simulation with mesh-less. What I mean is particles only. There will be people doing AMR, adaptive mesh refinement. There will be people doing multi-block, curvilinear grids, structured grids, etc. All those different grid patterns and data patterns will have to be taken care of. So if we have a generic interface to model this data, this will be very useful. In this third paradigm that I've already mentioned today, the in-transit visualization, we will have yet another issue. So if we review here, the first paradigm is to run your simulation on a certain number of steps and then do some visualization, save data to disk. Okay? Actually, here, save only the simulation to disk. In the inline visualization paradigm, we stop the simulation every n step, we apply some visualization, and then we save that to persistent storage. With in-transit paradigm, we use a secondary set of compute resources. We transfer the data to that second set of compute resources, and then we apply visualization. And here the question will be, is the time to transfer the data quick enough so that it's worth it to actually send the data to my alternate compute resource, or should I just as well do the visualization in line. So we'll have to verify that. Fortunately, today, with techniques such as GPU to GPU transfers, you can do very, very fast communication between compute nodes and between compute resources. So the transfer time is usually far less than the time you require for your simulation or for your visualization. Now, does in situ mean actually in place? There's a lot of different terms used: co-processing, in situ, in transit, in place, concurrent processing. All those words, if we send data to a second set of compute resources, is it still called in situ? Well, in our mind, as long as the data stays in memory, we call this in situ and in place. Okay. All right. So to try to clarify the taxonomy, clarify all this set of terms: runtime, visualization, co-processing. A study was made a few years ago, led by Professor Hank Childs at the University of Oregon, to actually make up a real taxonomy of the different techniques available. And for the scope of this paper, in situ processing was really defined to be processing data as it is generated. So this remains a bit generic, but it means that we process the data, I should say, while it's hot. Okay, there's no intermediate storing to disk and then reading back to another resource. So with this in mind, we looked at multiple factors. One of them is the integration type, meaning how is the visualization integrated with the simulation. Second item in the classification was the proximity. How far are we between compute resources? Is it memory to memory? Is it GPU to GPU? Is it across the node? Is it across different clusters? Access. Do we access data through pointers? Are we able to do zero copy memory sharing? Things. Division of execution, I've mentioned that already, is do we stop the simulation to be able to do transfer, to be able to do visualization, or do we run the visualization algorithm at the same time we run the simulation code? And then operation controls. This is interesting as well, because when we do in situ visualization, we lose some of the interactivity that we have with visualization apps. In visualization application, the standard way of doing visualization, you will load your data in memory, and then you have time to look at it, to think about what feature you want to extract. You have time to experiment with different features. So let's be concrete. If I have a volume of data, a scalar field, one of the classic visualization algorithm is to do isosurface computation. Now the question is, which threshold do you use for that iso contour? And this is where experimentation is very useful. You can try one particular parameter, one particular threshold. It will work well for a given time step, but perhaps 1,000 time steps from now, the same threshold will not work anymore. So again, you have to experiment. This is something you lose if you have a tightly integrated in situ visualization solution with your running simulation. So operation control is interesting. How do you interact? How do you modify the running script, etc.? And then the output type is also of interest. Do you save images? Do you save derived quantities, derived data? In the example of the isosurface computation, again, do you actually save the isosurface itself as a polygonal object, or do you save images? The drawback of saving a single image of an isosurface is that you will look at it after your simulation has run and you say, oh, I wish I had rotated the model by 30 degrees to see behind the isosurface. So you've lost that ability. If instead you save the isosurface as a polygonal object, then you have, again, the ability to move around that object. All right, so there's a few more details here about this taxonomy. I will go through those slides very quickly to actually get to the more interesting things of today. So as you see, there's really quite a few modulation, quite a few variation of all those different paradigms to the in-situ visualization landscape. And here's an example. When you do visualization, you want to do feature extraction. Well, what's a feature? Here is an example from aerodynamics. What is interesting is this wingtip vortex. Well, to actually look at this, you can imagine that I had to do quite a bit of interactive searching through my data set to be able to extract this feature. So this actually requires domain knowledge. If you are an expert in your particular field, you will know that some features are more interesting than others, and you need to be able to encode that into your visualization algorithm. I've said this already, this is where really we will miss the interactive feature of data exploration. And by the way, a feature like this can actually, even though it's a very small feature in terms of megabytes, it might be very expensive to compute. So we will have to look at this pretty carefully. All right. Now, at the time of the survey, there were 15 different systems that were reviewed, and half of them actually implemented a time division with on-node proximity. So this is actually the dominant paradigm which we will use today with Ascent and Catalyst. Time division means that the simulation will momentarily stop to activate a particular visualization algorithm. So that's the division of time. And we can do that every n iteration. And then the on-node proximity is the fact that we will use, and this is what Conduit will give us, you will see, the ability to share data via memory pointers, so without replicating data in memory. And this is very important with very large data. So we will use memory pointers to get very close access to the data. There are many systems today implementing some sort of in-situ visualization solution. Adios is one that we will mention at the end of this presentation today, because Adios is very, very interesting. Adios can integrate, for example, different data analytics while the data is being processed before it gets saved to disk. For example, data reduction, compression, data staging. And the thing that I will show at the end of the day, just to motivate you to stay alert until this afternoon, is the following schema here, where a parallel simulation using ADIOS in a traditional manner will write data to disk with a single flag which is switched on or off at runtime. That same stream of data, instead of going to disk, can go to another parallel consumer, which can itself execute a visualization algorithm. Or we can also stream data directly to an ADIOS plugin. This is what I will describe this afternoon. And that ADIOS plugin is also capable of executing a ParaView script. So there's here the distinction between classical I/O to disk and this particular mode of ADIOS called staging, where we do streaming of data between one running code and another running code on an alternate compute resource. Now, I've mentioned this briefly. Each one of you in your simulation code will have a particular internal organization of data. Okay, that's your data model. Perhaps you are familiar with the name structures of arrays and the opposite, which is arrays of structures. How do you store your data internally? Do you store the x, y, and z components of your velocity together? Or do you store all the x's followed by all the y's followed by all the z? That's the key point about, that's an example of the requirements of your application, which are exemplified in an internal data model. Well, the question is, will this data model fit actually the data model which the visualization algorithm expects? That will be the question to resolve, and if so, we have either the data adapters or the data converters to be able to shift data around. All right. In recent years, we've also done some new types of computation. Ensembles. Oh, I'm sorry about that. Ensembles, multiphysics, machine learning. I've heard the name probabilistic, fluid dynamics this morning. I have to understand what that means. So it's presumably not the standard simulation cycles that we are accustomed to. One grid of data, an iteration process, and you save your data to disk and you're happy. With those new forms of computation, we will have to adapt as well our paradigm, and the concept of a mesh of gridded points perhaps will be soon abandoned to have something more generic. So now is the time to really get into the details about Conduit, and you will see that those concepts will be made very concrete with Conduit. So Conduit came out as an open source project at Lawrence Livermore. Here I have to come back to my desk because I need to click on a couple of pointers. It's really, Conduit is designed to be an interface, a way of exchanging data between, generically speaking, a data producer and a data consumer. Okay? With interfaces in C++, C, Fortran, and Python. So most cases here are that will apply to your simulations are taken care of. And it's really about data coupling. Nothing more specific. For in-core, serialization, and I/O task. And building on top of this, we will have the visualization interface. Now, if Conduit is a generic way of documenting data, again, we have the question about if it's too generic, the data consumer will not know how to interpret the data. So this is why Conduit provides a convention to describe the more common computational simulation meshes, and that convention is called the mesh blueprint. So this is actually a point that we have, that we can click on the documentation here of Conduit, and it will explain all the details about the blueprint. The blueprint really is a way to say, I have data that represents a particular set of convention for a computational grid, and if my data follows that particular protocol, then everything is good. The data consumer will be able to talk to the data. The producer will be able to talk to the consumer. I think illustrations of blueprint examples are the best. And as we exercise Conduit here this morning with JupyterLab notebooks, we will be able to create some of those examples. There's a Conduit blueprint Python package which we can use. And here's an example of the basic class to generate an homogeneous example mesh with a given resolution and a given node. Let me browse further down the page and you will understand. This convention of usage will let me specify the mesh type. Is it uniform, rectilinear, structured, unstructured? Is it a mesh made of triangles, quads, polygons, tetrahedra, hexahedra, etc.? This will help us describe our data, our mesh topology. Further attached to a given mesh, I usually have scalar fields, vector field, tensor field. Those data can be stored at the node, at the vertices of the mesh, or at the center of the mesh. Echo. All of those details about your internal model for the computation will be described with the Conduit blueprint. And here's an example of a Conduit description for a given mesh. There will be a coordinate set of time uniform. So this is what we call the Cartesian grid. It's a two-dimensional grid. Dimension is 3 by 3. The origin of the grid is x, y. The spacing between each grid cells is given here with this particular keyword. And the fields, the association is element or vertex. And the values of the field are a given array. So those particular keywords here, those are the convention, the blueprint convention. Because we will see what Conduit is. Conduit is really just a dictionary, strings and values. But you can put anything in it. If instead you use those particular keywords, then your mesh will verify the blueprint and it can be read by Ascent. But I'm going a little bit ahead of myself. If we use the blueprint, then Ascent and Catalyst will be able to interpret the data as required. All right, so there's only one way to learn, is to do it by examples. So if you are able to connect to Conduit, I have already cloned the repository for you, so you shouldn't have to do that. And we're going to execute JupyterLab notebooks. If, however, you prefer to do this via the command line, via a terminal, you can compile all the Conduit examples in C++ using your account. So use your username, your account. The account is the group in which your logging name has been associated here at CSCS. So this is a fixed name for all of us. This is the command to run. What do we do here? We allocate a GPU compute node. We give it our account name, which is extracted. It's the same name as this CRS02. For 30 minutes, we use the debug queue, and we create a console on the compute node that is allocated. If we load all those modules, the Dane GPU module, the Ascent module, the CUDA toolkit, and the Crash HDF5 toolkit, then we can change directory to this particular directory and execute those commands to make the C++ examples. So all of those instructions here are in the notes. You don't have to copy them from the screen. If you are logged in on the terminal with your account credentials, you go to the slides subdirectory where the PDF document is located. And if it's not there, you need to do a git pull to refresh the content of the repo of the clone. And in that PDF, you will find those instructions. However, I'd rather go directly to the Jupyter examples because it's a lot more interactive. All right, so to go do the exercise with Conduit, with Jupyter, we need to go, you need to point your browser to this particular website, https://jupyter.cscs.ch. Use your credentials, your class username and your password, and I will demonstrate that to you as we speak. Then we'll go to the Ascent Intro Notebooks subdirectory, and we will execute that notebook number 2. So let me show you how to do this, and then you should be able to replicate that. So here's the interface to jupyter.cscs.ch. Here we only have to click on the button Launch JupyterLab because the GPU is the default allocation. One node is also your default. So I click on this and my credentials are already in the system, so I don't have to type them in. And here there will be 20, 30, 40 seconds of wait perhaps because we need to allocate the compute node. Once we are allocated, you will see that the display will change, and then you will have access to your home directory. In that home directory, you change directory to the notebook examples, and we will be able to execute them. So Conduit, as I said, is simply a dictionary, just like a Python dictionary, but a little bit, quite a bit more than a Python dictionary. There, you see this is coming up. There we go. Here's the interface to Jupyter Lab. I have here a particular kernel called the CSCS Python kernel, and this is what we will use. Your account has been set up for this particular kernel. So let me demonstrate that over here. Okay, I went a bit too far. Here's you should find in your home directory this folder. Okay, this is what I have cloned from my repo. You need to click in there, go to the Ascent introduction, go to the notebooks, and then execute number 2, the Conduit Basics notebook. I'm going to run a couple of cells here, and then we will wait for people to be able to do the same demo by themselves on the computer. All right, so my very first cell is pre-classic. I will import Conduit, and I will import NumPy as NP. There. Success? Yes. Make sure that you are using the correct Python kernel. If this gives you an error, it's because you are using an alternate kernel. So it's pretty simple. You go to this, and you can see here that there's actually a choice between different kernels. You need to select the CSCS Python kernel for that. So I'm all set up over here. Let's do the second cell.
Hello?
And this, all of you, if you've used a minimum of Python, let me finish the sentence. You will be familiar with this. This is the standard Python instruction for dictionary. You give it a key, you give it a value. Let me execute this, and sure enough, when I print that Conduit node, it has a key that references a given value. That given value can be a string, a numerical, a number, or an array, or anything else. All right. I think now we can stop the video. We will run that exercise, make sure everybody can access the notebooks and do those different exercises.